All right, so we're going to start talking about chapter 5 in the textbook, and this chapter is all about logarithms and exponential functions and how we take derivatives and integrals when working with those types of functions. So what I want to start talking about is the function 1 over x dx. And if you think about what happens if we were to try and integrate that function, you could think of it like a power rule as x to the negative first. But if we apply the regular power rule, the problem is that we end up with x to the 0 over 0, which certainly doesn't work. But this is still a function that has area contained underneath it, and so we want to be able to integrate it. So here's what we're going to do. We're going to define an antiderivative for this function. So the integral of 1 over t dt from 1 to x is the natural log of x. So you'll jot that down in your notes. We're going to use that quite a bit in this chapter, so you'll get used to seeing it. I want to remind you of a few properties of the natural log function. The domain of the function is from 0 to infinity. So remember, you can't ever take the log of a negative number. And the range is all real numbers. The function is continuous. It's increasing the whole time. We said that was monotonic. We used that term earlier in the year. And it's one-to-one, meaning it has an inverse. And if you'll think back to pre-calc, a function is one-to-one, and we can check that by the horizontal line test. And it's concave downward. Here's a little sketch of the function to make sure you see that all of these things apply that I'm talking about. A few properties of the log functions. Natural log of 1 is 0. Natural log of AB can be expanded as the natural log of A plus the natural log of B. Power rule, natural log of A to the n, can be written as n times the natural log of A. And that quotient rule, the natural log of A divided by B, can be expressed as the natural log of A minus the natural log of B. So we use these properties to expand and condense logarithms. And you might have wondered back in algebra when you were doing those what the point of all those rules were. And you'll see as we go through this chapter that it makes the functions easier to work with very often if we can expand them. So we're going to use these properties quite a bit. Let's do an example here. Expand the logarithmic expression natural log of the square root of 3x plus 2. So if you'll recall, you write that as natural log of 3x plus 2 quantity to the 1/2 power. And because that's a power, you can write that in the front, and that's completely expanded. Another one a little bit more complicated. Natural log of x squared plus 3 quantity squared divided by x to the third, that's the cube root, x times the cube root of the square root of x squared plus 1. Make sure you write that as the cubed root. Kind of hard to tell, but that's what they meant for it to be. So since we're dividing these two expressions, the first thing I would do is change them to subtraction. And the second two expressions here, since those are being multiplied, we can change that to addition. But notice I put brackets around these two terms because that negative is going to have to be distributed. Also notice this power of 2 I took to the front here. And since I have the cubed root of the x squared plus 1 expression, I'm going to write that as x squared plus 1 to the 1/3. And notice I also went ahead and distributed this negative. And if we bring that 1/3 to the front, that's completely expanded. So if the integral of 1 over t dt was the natural log of x, then the derivative of the natural log of x is just 1 over x. So memorize that, make sure you know it. Like I said, we're going to use it quite a bit in this chapter. So let's do a couple problems here. Find the derivative of the natural log of 2x. We could actually expand this into the natural log of 2 plus the natural log of x. And the natural log of 2, the derivative would be 0. We're just left with natural log of x, the derivative is 1 over x. But if you didn't think to expand it, think of this like a chain rule, where 2x is the inner function, natural log is the outer function. We're going to write this as 1 over, so derivative of the outer, evaluated at the inner, so 1 over 2x times the derivative of the inner, which is just 2. So those 2's cancel, and we're just left with 1 over x. Try the natural log of x squared plus 1. So we're going to do 1 over the inner function, x squared plus 1, times the derivative of that inner function, which is 2x. Last example, natural log, or x times the natural log of x. Notice that this is going to require a product rule. The derivative of the first times the second recopied, so 1 times natural log of x, plus the derivative of the second, which is 1 over x, times the first recopied. To clean that up a little bit, we just get natural log of x plus 1.